So asymptotic solve is asymptotic solutions of algebraic equations. So the function takes an equation and a system of equations, the value of one variable or a set of variables, and the point. So xy is a single solution point of this equation, of system of equations. And we would like to get an asymptotic expansions of y in terms of variable x to the n terms. Now, depending on what kind of situation we are, those things will have slightly different meanings. So let me start with the simplest situation where we have a non-singular point. So the equation is, and also a single variable. So in this case, we have an equation with two variables. It's an analytic equation. We are at a point where the function f is analytic. And so by implicit function theorem, we know that near this point, the solution of y can be expanded as an analytic function of x. And here we are getting the regular series. Now we get a series in x. And there is exactly one solution also. So we can compare the solution and the numeric solution. You can see that we can also use the solution to get the numeric solution. So we get the starting point for find root as the value of this asymptotic solution. And we plot the solutions. So you see they're almost completely equal near the point 0, 0. They start to diverge around x equals 0.4. So now the more difficult situation. So again, we have two variables. We want solutions for y in terms of the variable x. But now the function is singular. So we have a multiple solution. And now what we can hope for is a system of Puiseux series. So you can see we have, so this function, see if we set x goes to 0, we get y to the 7th power, so it's 7th degree solution, and it splits into two analytic solutions, one of degree 3. So this is the denominator 3. We got three solutions with powers with denominator 3, and 4 solutions with powers with denominator 4. So we get 7 solutions, and they are Puiseux series. But they are still nice series. They are convergent series near the point xy equals x0, y0, in this case 0. And we are also able to find the solutions with real coefficients. So here is the version with real. Only 3 of those solutions have real coefficients. So in this case, we cannot really say that they are real solutions. They have real coefficients, and they will be real for positive value of x. For negative values of x, they will be complex in general. So here are the real solution for, we graph them for positive values of x, and again we can see they are very close to the numerically obtained solutions. So they are pretty close to the actual solutions, and we can also see that now it's very useful to have this asymptotic solution. We could find the numeric solution using them as starting points, and we could find the actual three numeric solutions using the starting points. So the next case, the level of difficulty is so we have algebraic curves in n dimensions. So we have n variables, n-1 equations, and we want to get solution for all variables except one in terms of the first variable. So here we are looking for solutions for x and y in terms of the variable z. And here they are. Again, this was a singular point. We got Poisson series. But in this case, also the Poisson series is the worst we can get. We always will get solutions with fractional powers. Plot the solutions, and here they are. We can see there are four solutions, and close to zero, they are the asymptotic solutions are very close to the numeric solution. One of the solutions actually quite starts diverging from the actual solution quite early. So different solutions can have different rate of convergence to the actual solution. So now for possible extensions, so this is as much as we have right now implemented of this function. So the harder cases now. So analytic curves in n dimensions. So this particular thing that I showed for n dimensions, actually I used the fact that the system was polynomial. So for the curve in 2D, I could use arbitrary analytic functions. Here I actually use the polynomial system. I used elimination to get a single equation. So, but in general, it might be doable using Newton polygons, polytopes. Polygon is for 2D case. Now, the more difficult case again. So, k-dimensional. Well, actually, this one is the smooth surfaces are not difficult. So we can have in n dimensions we can have n minus k equations, and we are and if the system is non-singular, so the derivative, the determinant of the derivative is not zero at the point, we can use the analytic implicit function theorem and get the actual analytic parametrization of the surface. So that's the nice case. Now the singular cases are more problematic. So the singular surface in n dimensions, first it can split into several pieces with different dimensions. So that's the first difficulty. But even an irreducible piece, it doesn't necessarily have to have the description in terms of a convergent power series or Poisson series. It may have piecewise Poisson series or fractional power series that are convergent in some cones, but in general it will be piecewise solution. So that's the hard case, and also going to analytic functions instead of polynomials, that's also hard case. An even harder case, so the next one is asymptotic expansions at infinity or at points at which the system has singularity. So not the solution has singularity, the system has singularity. So the function describing this has a singular point as x0, y0. So that's even harder case. And in this case, we are not even getting a power series. We will get actual asymptotic series, meaning we get some functions that asymptotically tend to the solution, but they are not power series. So this is what I have about solutions of algebraic equation. Devendra will continue with integration and differential equations.
I'll now go on to the kind of calculus side of things, and I'm going to talk about two functions: asymptotic integrate, which finds series expansion for integrals, and asymptotic desolve, which is series solution of differential equations. So asymptotic integrate is just like integrate. So you have an expression, you want to integrate over a certain interval, but you also have a certain parameter in the expression or the interval, and you want to do an expansion with respect to that parameter. So that's just an extension of integrate to handle cases where you only have a series expansion possible. So two examples to show what's happening over here. Here is a complete elliptic integral. So that's the complete elliptic integral part, the first two arguments. And your parameter m, so you want to expand with respect to that parameter, and you get back a series from asymptotic integrate, and you can compare that with integrate. So in this particular case, integrate does work, and you get back the elliptic integral, of course. You do a series expansion, and you get the same answer. So that's one way of looking at the asymptotic integrate. But the other way is to look at n integrate, its numerical counterpart. So here's an example where you actually have an exponentially decaying function. So here's the plot of the function, and I want to find the tail end of the integral over here. So what I do is I do an asymptotic integrate, but this time it used repeat integration by parts. So what you get back is not a power series, you get back an asymptotic series, which is still good, but more useful for numerical work in this case. Okay, so now compare with n integrate, and you get a, as you can see now in just a minute, you get a pretty good approximation with the asymptotic solution. So that's the idea. You have a series expansion, either use it directly or do a numerical evaluation with it. Okay, now historically, the two most important methods beyond what I just showed you are the Laplace method and stationary phase method. The Laplace method is due to, of course, Laplace. And what Laplace said is that if you have an exponentially decaying function, like a Gaussian function maybe, and it has a maximum at a certain point, in this case, the maximum is at 1, you can do a series expansion around that point and get a result for the integral. That's a pretty hard integral, actually, but you get back a nice expression, just a single term, and that single term is pretty good for giving you an approximation of the integral. But if you want to go a step further, with more than just one term, you can also do 2 terms, or 3, or whatever you like, and you can see that early on you had a slight discrepancy between the exact, between the approximations over here, and now that discrepancy just goes away. So just a single term in the expansion, a single extra term, gives you a good answer. And that's the magic of asymptotics. Okay, so that's Laplace. And then what Stokes said is, okay, let's do the same thing for oscillatory functions, like, sines and cosines. So here's an oscillatory function, and that's the real part. And what you notice is that all the action is around the maximum at pi over 2. This is kind of, right? So what you do is you do an expansion around there, the same trick, with what you do with Laplace, and lo and behold, in just a minute, I'll be able to show you that you get back an approximation. Now that approximation is pretty good. It's oscillatory, so it's not so easy, but you do get back an answer. And to go beyond that, what you do is you transform to the Laplace case, the good old trick of converting a complex integral into a real integral, and you get back a nice answer. So that's asymptotic integrate in a few minutes. And I now go on to asymptotic desolve, which is the other function which I've been working on. And this is a kind of complete solver for all kinds of series solutions. Ordinary points, regular singular points, irregular singular points, nonlinear ODEs, systems of ODEs, everything is already more or less working. So some examples. But first of all, what's the function? Very simple function. You have a differential equation. You have a dependent variable x, and you want to find a series expansion. People have written these for a long time on their own. This is now our own implementation. Okay, so ordinary points. So now here you have no particular problem in the equation. There are no singularities in the coefficients at 0. So you get back a nice Taylor expansion, and that Taylor expansion is easy to plot. You get back lots of approximations. That's a textbook example of solutions at an ordinary point. Okay, so next I go on to regular singular points. And now things get a bit harder because what you have is a singularity in the coefficients, but it's pretty mild. So you have an x square in the leading coefficient. You divide through by it, you don't get a bad singularity. And in such a situation, compute the Frobenius series solution, and we give back the answer. But now you don't have a power series, you have a square root of x over here and a 1 over x over there. That's the Frobenius method from college calculus. So ordinary point done, regular point, singular points done. How about irregular? Well, for that, I thought I'd choose the Airy equation, which expands to infinity. So now this Airy equation is well known to have an irregular singular point at infinity. So if you do x equal 1 over t, then you get back an irregular singularity at 0. Okay, so here's the answer for the expansion. There are 2 parts. Each part is an exponential, and a kind of Piso series. And what the exponential is, it's a factor which will reduce the singularity down to a regular case. That's how you think of that exponential factor. Okay, so now you do a comparison with the Airy function. You see you get exactly the same answers for each component over there. One of them is Airy AI, other one is Airy BI. And if you plot them, then because you're at infinity, initially the expansion doesn't match, but at infinity, each expansion, each approximation clings on to the correct function. So it's pretty remarkable how nice the answers are when you start working with them. And of course, this works blindingly fast. It's a general algorithm for holonomic ODEs, for irregular single point holonomic ODEs. So you can do order 7, 10, what you like. It all works blindingly fast. And finally, here's an example of a nonlinear ODE. And what I do nowadays, when I get an example of this type, I just give it to my new favorite function. And you see I've set the number of terms to 32. But what you get back is in fact when it finishes, a quadratic polynomial. So that is an exact solution. The solution is a polynomial solution, and we found it now. Okay, so I checked the solution is correct, and I have found an exact solution using an approximate method. I have an example that's similar, where we get back the right answer with the asymptotic method. Okay, so now I go on to perturbation expansion. That's the other side of the story, where you have a perturbation parameter in the problem in addition to the independent and dependent variables. So here's an example, the Duffing equation, that's an oscillator. So you expect a periodic solution, and around 1890 or so, Ponkler and Lindstedt worked out the so-called Ponkler-Lindstedt expansion for these things, where you get back periodic things in your perturbation expansion. Notice how simple it is. It's just got two terms in it, a cosine term and a sine term, whatever, and then epsilon times something else. But that is good enough to capture the solution to a pretty good extent, because if I now compare to the exact solution from DSOL, which took a lot of work to get done, it's got Jacobian elliptic functions in it. That's a mess, and still gives you roughly the same answer. Okay, there you are. So 2 terms of perturbation is good enough to match your elliptic function solution. Okay, so my final example now. That's with boundary layers. So roughly speaking, boundary layer theory is what you do in fluid dynamics, where Ludwig Prandtl in 1904 wrote a paper on, he said that if you have a viscous fluid and you've got, let's say, a wing or something that's passing through it, then all the action takes place in a small, thin boundary layer around that body. So you have a separation of the fluid into an inner layer and an outer layer. And what you want to do is you want to match those 2 expansions and get a nice solution. So around 1940, Kurt Friedrichs came up with a very simple example that's over here. So the problem is you have the parameter epsilon over here. So if you set epsilon to 0, things go wrong. So that's a singular perturbation problem. Fortunately, we have the WKB method from quantum theory, which gives you a really nice solution in this case. A linear approximation, a first term approximation. You plot it, so you find table of values, compare with DSolve, or DSolve value in this case. You get back almost the same solution numerically, but look at the complexity of the approximation versus the exact. And in fact, if you plot them both, they look almost identical. And the reason why they look almost identical is because I added the plus 0.01 over there. If I had not done that, they exactly match. So with just a single term in the perturbation series, we have got so much power of computation.